Okay, benchmark 5.2 for geometry. We have special triangles that we're working on here, the 45, 45, 90 triangles and the 30, 60, 90 triangles. I have some extra problems if you want to check out the other link on my webpage on more special triangles. It's from chapter 10. It's just like this, and I was going to replace it with this, but I figured you'd have a few more to look at. This is set up just like the benchmarks. So with the 45, 45, 90, I want you to imagine it's half of a square. Okay. So, and we're going to cut this square in half. So you always know that these two sides are the same length. And if we use the Pythagorean theorem, we'll find out that that third side, or that hypotenuse, is always whatever a leg is times the square root of 2. So even if that leg is like 8 square roots of 3, you still have to take that, squeeze it in for x up there. So we'd have 8 square roots of 3 times square root of 2, and we'd have to simplify that stuff. So we have some interesting problems to work on here. So first one, we have 7 square roots of 2. So going to the hypotenuse, it's that 7 square roots of 2 value times the square root of 2, because that was our process. The process is times the square root of 2. So when we simplify 7 square roots of 2 square roots of 2, we combine those together. That's the square root of 4, which is just 2. So we get 7 times 2. So 14. So x is 14 in this particular case. Our y value is the same as the original, because those are, again, we're thinking of this as being half of a square. So that's 7 squares of 2. That's 7 squares of 2. Okay. Let's get rid of some of this. I'm going to jump over to the other. Oh, we only have one other one. Down here, this number 5, we have a 45, 45, 90 because I have the two sides marked equal. So that must be half of a square. So this must be 45 degrees and 45 degrees in the two angles here. And if you look at this one, I'm going backwards. I give you the hypotenuse, and you have to kind of work backwards to figure out where did it come from. So I have this. Luckily, in this problem, it has just 9 square roots of 2. Going backwards, we can just kind of do it in our head. We know that that's just going to be a 9. But process-wise, because it's not always going to be this easy, you need to know that if you're going backwards from the hypotenuse back to the original, back to a side, a leg, we have to divide by the square root of 2. Instead of multiply by the square root of 2, which is going forward, we go times the square root of 2. When we go backwards, we divide by the square root of 2 to get back to x. Well, so divide by the square root of 2, we can rationalize here and stuff, but we just notice that these two just cancel. Okay, so we just get 9. I'm sure we'll be rationalizing in a couple of these other problems pretty soon here. So that's the answer there, 9. So both of these are 9. And that's all of them. So we'll just go to the 30, 60, 90 triangles. I'm skipping number 2 because it doesn't tell us the angles right there. So we'll come back to that later. It's a different type of problem. But this is a 30, 60, 90 triangle here. So there's my 60 degrees. To refresh our memory here, I want to imagine this being half of an equilateral triangle. So if this was, let's say, 10, 10, and 10, 60 degrees, 60 degrees. Well, when I look at just half of it, let's say this half, well, my 10 over here, this turns into a 5, because it's 5 and 5. And then if I use the Pythagorean theorem, I do 5 squared plus x squared here to get 10 squared. That x will be 5 square roots of 3. It's always this little short side times the square root of 3. So that's why when we show you these little formulas up ahead of time, when you see this thing, we have x, this is twice as long, like that 5 and that 10, and this was x times the square root of 3. It doesn't have to have a square root of 3 in the answer, it just means the process is multiplied by the square root of 3. Now, yeah, the hard part I think here is visualizing or rotating this triangle, that number 3 here, just so it's looking the same as my original picture right here, because it might be flip-flopped or rotated. But if you just always realize, oh, this is the hypotenuse here in the 30, 60, 90 triangle is always twice the length of the short side. So if this is 8, this has to be a 16 here. And then the process is take the short side times the square root of 3. So it's 8 times the square root of 3. We can't simplify that, so we're done. Let's go to number 4. Another 30, 60, 90. Here's a short side. Here's the hypotenuse, which is twice as long as the short side, the 30, 60, 90 triangle. So just take 3 squares of 2 and I double it. I'm going to put the times 2 out front just because I know I can combine those two together. So 6 squares of 2. And that's it. The other leg is times the square root of 3 from the short side. So I'm going to take my 3 squares of 2. I'm going to multiply that times the square root of 3. Because the process is always take it times the square root of 3 from the short side. And that's what I'm going to do. Now, if you're able to, go ahead and combine. Like I had a square root of 2 to begin with, so now I have 3 square roots of 6 as my answer up there. Now, if this was 3 square roots of 20 or 3 square roots of 18 or something, I could break this down. Okay, and I think in my other video I explained that a lot more. These are pretty straightforward ones. On the benchmarks, they're pretty basic ones. You're not going to have to do a lot of reducing and rationalizing of the denominator. It's just, do you basically understand how the process works? And this is as hard as they're going to get on these. Now, when I look at number 2 and number 6, these are a little different. I'll erase all this stuff here. Looking at 2 and 6, they don't give us angles. So my first thought is Pythagorean triples. Do you know your Pythagorean triples? Pythagorean triples are like 3, 4, 5 triangle. In other words, 3 squared plus 4 squared, that is 5 squared. It works out. What's some other ones? 5, 12, 13. Okay. Pretty much if you know these two, you'll get most of these right on the benchmarks. And because if you know 3, 4, 5, you know all the multiples of those. If I double the 3, 4, 5, I have 6, 8, 10. If I go 3 times 3, I get 9. 4 times 3, 5 times 3. So 9, 12, 15 triangle. So those kinds of things. And then same thing over here. 5, 12, 13, I could go 10, 24, 26. And all multiples of those. Okay. So when I'm looking at this right here, I have a 15 and a 39. My first thought is, well, they're both divisible by 3. So if I divide the first one by 3, I get 5. If I divide 39 by 3, I get 13. Well, I'm looking at this now. I see a 5 and a 13. So this must be like a 5, 12, 13 triangle. 5, 12, 13. Well, it's not really 5, 12, and 13. It's 15 something 39. But each one of these is 3 times as large as the 5, 12, 13. So if I take my 12 and I triple it, I'll get 36 for that side. So there's really you don't really have to show any work for this. Just know that this is part of a Pythagorean triple. If I continue this process right here, I'll get to, well, if you look at that 5, 10, 15, 12, 24, 36, 13, 26, 39. So there's a triangle I just did right here. Looking at number 6, kind of the same process. Well, I see that 24 and 32 are both divisible by 8. So if I divide this by 8, I get 3. If I divide this by 8, I get 4. Oh, that's a 3, 4, 5 triangle, looks like, because it's leg, leg, hypotenuse. Well, if it's a 3, 4, 5 triangle, and I use the same ratios, I need to multiply that 5 by 8. I should get 40. So it's really a 24, 32, 40 triangle. If I take 24 squared plus 32 squared, I should get 40 squared. All right, that should do it.